Hello and welcome everyone. Thank you for joining us today for our webinar titled Deploying Distributed AI and Machine Learning in Financial Services. My name is Shabar Pula and I'm on the marketing team here at H2O.ai. I'd like to start off by introducing our speaker. Dmitry Bayev is the Vice President of Solutions Engineering here at H2O.ai. Before I hand it over to Dmitry, I'd like to go over the following housekeeping items. Please feel free to send us your questions throughout the session via the questions tab in your console. We'll be happy to answer them towards the end of the webinar. This webinar is being recorded. A copy of the webinar recording and slide deck will be available after the presentation is over. Without further ado, I'd like to hand it over to Dmitry.
Excellent. Thank you, Shabar. Just a sound check on my side. Can you hear me? I'll take that as a yes. Good morning, good afternoon, good evening, everyone, depending where you're joining us from, depending on your time zone. My name is Dmitry Bayev. I'm the Vice President of Solution Engineering here at H2O.ai. And today, I'd like to talk to you about deploying distributed AI and machine learning in financial services. Some key takeaways that I would like for everybody to be able to walk away from this webinar is we're going to take a look at how do you train machine learning models at scale using distributed big data platforms. We'll talk about how do you apply automated machine learning or AutoML to accelerate your model development pipelines. We'll talk about how do you actually then take those machine learning models and you deploy them into production environments. And finally, we'll take a look at a few financial services success stories where AI was really the main mover. And I'd like to start with a quote. This is a quote by Archimedes, who was a Greek mathematician, a physicist, engineer, inventor, and an astronomer. And he said, "Give me a lever long enough and a place to stand, and I shall move the world." And the parallel here, the analogy is that that lever is your data. We work with many customers that are embracing themselves, that are going through AI transformation journeys, and it always comes down to these three foundations. It's the data, it's the AI as the technology, and it's the people as the talent. And it's really about your data. So as thinking back to that quote, that lever is your data. The data is your leverage. And fortunately, in financial organizations, financial organizations have vast data reserves. Over the last many years, many of the banks or the financial service companies that we are working with have embarked on various data lake journeys. So the idea there was to break down the various data silos that exist in large financial institutions to be able to bring your data together as it spans in maybe consumer banking, maybe wholesale banking, maybe capital markets, financial trading applications, as well as a lot of other operational data sources, right? Something that is known as defensive data sources, so things around ML, fraud, compliance, cybersecurity. And the idea there is that by breaking down those data silos and by actually being able to bring the data together into some form of a data lake that could be manifested as a distributed Hadoop cluster, could be a Spark cluster, could be running on-prem or in the cloud. But the idea there is that you now have a lot of different types of data all coming together into this distributed environment. And how do you now actually apply AI and machine learning to take advantage of all this data across the distributed environment where you've got terabytes and petabytes of data, as well as many distributed machines that all together can provide you with an extremely robust and extremely powerful computer environment for running your machine learning workload. And that's exactly what we're going to explore going forward here. But before we dive in deeper into machine learning, it's important to understand and to really look at this data science hierarchy of needs, the pyramid, to realize that the foundation here is all about data management and data engineering. So if you look at the bottom layers, it's all about collecting the data, moving and storing the data, then going through the process of actually refining, cleaning, and prepping this data such that you can then further move into those higher value workloads for data science. And hence, we always say that effective AI and ML requires a solid data foundation. And that's exactly where H2O.ai really plays in this data science domain that really allows you to take advantage of all the vast data reserves that that financial companies, banks and other financial institutions accumulate over a period of time. From a technology perspective, H2O.ai, our AI and ML platform, is really composed of 3 key capabilities, and these capabilities have been evolving, and we've been building this out over time. If I start on the left-hand side, this is where the foundation of the company really came from. So since 2012, H2O has been building the core functionality, which are all the different distributed machine learning algorithms that can run at scale across distributed environments, fully in memory. So it allows you data scientists to leverage Python, R, and other programming environments, programming languages, and programming environments to get access to the latest and greatest distributed machine learning frameworks. And we'll talk about the different algorithms that are available as part of the H2O library. We then expanded that reach to integrate with the Spark ecosystem because, as Spark became more prevalent when it comes to data engineering, we really looked at how do we integrate the 2 ecosystems such that you don't have to go back and forth between doing your data prep and data engineering using Spark and then core machine learning using H2O. And that's where Sparking Water really came about. So Sparking Water is a library, is a framework that actually unifies these two programming environments together, and we'll take a closer look into how seamlessly you can go between writing Spark applications and then building your machine learning models using H2O. So H2O at its core is all about algorithms. And then we took a lot of the learnings that we've done and that we got from customers, a lot of feedback from data scientists that had to go through a very powerful but a very manual process of actually writing their applications by hand using R or Python, going through feature engineering, feature selection, and all the tedious, very iterative steps that typically go into a machine learning lifecycle. And we've then took that into H2O Driverless AI to create an automated machine learning platform that really automates a lot of these manual steps for you. And it focuses on automated feature engineering, on model selection, tuning those models, building the ensemble of different models, different techniques, and then actually creating the final model pipeline, what we call a scoring pipeline, that is fully ready to be deployed into production with explainability, with interpretability, and auto documentation that is very much needed in what I would say in every industry, but even more so in regulated industries such as financial services. So Driverless AI is really about accelerating your machine learning models, or accelerating the pipeline of allowing you to build these machine learning models at a much faster pace, so condensing the time to value. And then the third piece, which we are evolving towards, is we call it H2OQ, and this is all about democratizing AI. So now, as we've gone from the low-level algorithms with H2O Core to machine learning models with Driverless AI, now we're really focusing on how do we deliver AI applications such that we can truly democratize AI across your business, across the bank, and really empower your business users and the business stakeholders who don't have the chops and who don't have maybe the classical data science or statistical training to be able to leverage the applications and to really focus on solving their business needs. So with that in mind, we'll dive into more details, and let's start by looking at what H2O Core really brings to the table. So as I mentioned before, it's an extremely scalable machine learning platform that provides a number of very robust algorithms. Each one of those, so whether it's a GLM or a GAM or distributed random forest, XGBoost, so on and so forth, each one of these algorithms is designed from the ground up to work at scale across a distributed cluster. So if you are a data scientist who prefers to program in Python or R and really wants to be able to have all the vast compute power to be able to crunch machine learning models against full scale, so terabyte or petabyte scale of data without having to sample and really having full access to full fidelity of data, then H2O core is a great choice because as a data scientist here on the left-hand side, you are able to program with your familiar languages and IDEs, so Python and R, Jupyter and RStudio. We also provide a web user interface called H2O Flow, which is more of a point-and-click interface. But in either case, you have access to a variety of H2O algorithms, both supervised and unsupervised, with very consistent API that you can invoke from your preferred language and your preferred IDE. And what you don't have to care about is how does the infrastructure, right? How does the compute, how does the distributed nature of H2O really gives you access to all of the data and all of the compute that is available in the distributed cluster of nodes. So what you have on the right-hand side, this is a representation of a typical Hadoop cluster architecture, but as I mentioned before, H2O is designed to run at scale across any distributed framework such as Hadoop, Spark, or even Kubernetes. It can run both on-prem or in the cloud. And in case of Hadoop, for instance, where you've already went down the path of creating this enterprise data lake where your data is sitting in HDFS, H2O dynamically spins up the cluster where you can sort the data from HDFS. That data gets loaded into memory, and you can actually now start processing, doing all of the math calculations as per the model that you've selected, whether it's a GAM or a GLM or a distributed random forest, right? Whatever technique you're choosing to apply. Now, so with that high-level architecture in mind, let's actually dive in a little bit deeper, and let's take a closer look at what it actually takes for you to go through a single experiment, through a single cycle of running H2O distributed machine learning, on a distributed cluster. So first step, you would obviously load the data. The data gets loaded either from HDFS, could be S3, could be other data sources. The part of the loading process takes the data from disk, distributes this into memory. We use a lot of different lossless compression techniques. But at the end of the day, as a data scientist, all of that complexity is hidden away from you. And your first foray into interacting with H2O is really through your favorite IDE or through your favorite notebook environment. So for instance, if you are a Python programmer with Jupyter, you'll use Jupyter as a notebook environment. You'll start doing different exploited data analysis, feature engineering, feature selection, maybe try different types of supervised and unsupervised models just to see and compare the different model evaluation metrics, such as maybe AUC or RMSC. And it's a very manual process where you're in full control and you can really tune all of the parameters of the model by hand. And at the end of your experiment run, what you end up with is an H2O model, something called a mojo. And the mojo is basically, think of this as a binary representation of your model with a very thin runtime. So that means that model can be easily deployed into any Java-based, C or C++-based runtime, with very little dependency other than the actual runtime binary itself. Now, and we'll come back to that example in more details, but now that you have a basic understanding of what it takes for you to run through this, through a single model experiment, through a single model build process, and you have that H2O mojo file, which is the H2O model file, we can now start talking about how you will take and, for instance, deploy that model using Spark and Water. And in a very typical scenario, you may have a data source. So that data source could, for instance, be either inside of your data lake, so maybe it's on HDFS, or maybe the data is sitting in S3 or other JDBC data source. Could be a relational database or a warehouse. And you would leverage Spark, which is a very common technique for doing data engineering. So Spark is great because it uses the same concept of distributing processing. The data gets loaded into memory using Spark data frames, and then you can do all the data engineering and all the data munging programmatically using Spark. But once you're actually ready to then start training your model, what you need to have a gateway, an easy way to call any of the H2O algorithms that we just discussed previously, And that's where sparkling water comes in. So sparkling water is a very thin wrapper or an API that allows you to invoke H2O model building code from within the Spark pipeline. And what happens at this stage is that now that you have all of your data loaded into Spark data frames, that you've munched the data, you've gone through through all the refinement process. Now, by calling the Sparkling Water API and telling it to go and train the model using, for instance, H2O GBM, which is a gradient boosting machine, for example, now the data is moving in memory from Spark data frame to H2O data frame completely seamlessly and invisible to you as the end user, as the data scientist. But the training process is kicked off with a single API call, and again, what you end up with is you have this binary representation of the H2O model, where that module file is now fully ready for you to take it, and you can deploy it into any environment that you like because you're in full control of how that model gets deployed. So if I take that example now, deploying that model for the scoring process, now I have my new data, unseen data coming through a data stream. So this could be a Kafka stream, or maybe this is a Spark streaming application where I'm now getting new data, and I can pull one record at a time, or it could even be batch scoring. So it depends on the application. Both real-time and batch scoring can be done this way. But now you've got your Spark front end that is collecting the unseen data, right? So the new events that you would like to score, and invoking the H2O model through the Sparkling Water API such that this unseen data gets scored against the module or the H2O model, and now you have some sort of a business a prediction which can be used for business decision making. So depending on whether this is a binary classification problem, right, or maybe some sort of regression problem, you now get a score that would be meaningful for you in a business sense. Now, this is a very simple example, but if we start looking at enterprise machine learning workflow, obviously it gets a lot more, what I would say, a lot more complex. It's very iterative and a very tedious process that starts with a business analyst on the left-hand side, where you start looking at how do you define your business problem. You then go through many manual steps of sourcing the data, prepping the data with the data engineer, and then you continue the process with the data scientist, and finally with the DevOps engineer who's going to take that model and deploy that into production. As you can see here, even without getting into too much detail, it's a very tedious process that involves a lot of handshakes and a lot of coordination between different, not only different people, but also different skill sets and different personas. Now, if I zoom in and I only look at the data scientist's responsibility, right, things become even more complex as we now start thinking about different feature engineering techniques. And by feature engineering, what you're really trying to do is you're trying to amplify the signal. So you have a lot of data, right, and it's especially true when you're working with distributed big data environments where you now have the luxury of tapping into terabytes or maybe even petabytes of data, and obviously a lot of that data may just contribute to additional noise. So through the process of feature engineering, you're really trying to look for data transformations that would allow me to identify and amplify the signal while being able to discard the noise. So many different techniques when it comes to advanced data transformations, advanced encodings, to be able to generate those features. And then from the multitude of generated features, how do I now actually select the features that will be most relevant and most important for my model building without overfitting to all these features that I may have created, and my model just inadvertently learned the behavior of those features without being able to actually generalize. So that requires time, and that requires advanced skill set in order to be able to truly understand and to truly wrap your head around feature engineering in a sense where it provides a lift to the final model. Then the same story continues. So then you go through the model building phase with algorithm selection, tuning those algorithms. Every algorithm may have its own parameters. So not only you need to understand the algorithm itself, but you also need to understand the various parameters and how they affect tuning of those parameters. how does it affect the final outcome. In many cases, building model ensembles can actually produce, on one hand, it gives you could give you a lift, so more accurate models, but on the flip side, it also creates more complex models. So in regulatory environments, you obviously want to maximize the accuracy of the model, but if the model cannot be explained or if it becomes too cumbersome to understand, you may have model risk and model validation teams that will be questioning the validity of that model, especially in regulatory environments such as financial services. So that's where on the model deployment side, things such as pipeline generation, so taking my data science code and actually recoding it in a production language such as Java or C, C++, being able to explain my model and having accurate model documentation, proves to be another challenge that requires another set of skills. And again, it's extremely time consuming. And all of that is a clear call for automation in machine learning. And HTO has been in the space since 2012, so we have a very rich history, and we really think about automated machine learning in multiple generations. So Gen 1, and this is what HTO AutoML, which is part of open source, delivers, it allows you to go through automatic model selection, automatic parameter tuning. It applies different grid search techniques. So with few simple clicks, you can basically tell the algorithm, HTO AutoML, what algorithms it should consider, how long it should run for, how it should tune those models. You can maybe even specify the grid search for AutoML to chug through. But at the end of this run, however long it takes, what you end up with is you get a model leaderboard, which provides you with the performance metric of each individual model. And then from there, you can pick either a model that provides you with the best performance metrics, or maybe you have a preference to a certain model technique because it's more explainable, in which case you may be willing to jeopardize a little bit on model performance, but you might be able to pick a model which is lower on the leaderboard, but yet still gives you excellent performance with combination of explainability. And we really think of this as the first generation of automated machine learning. The next step here, and that's where HTO Driverless AI really comes in, it's all about machine learning recipes, right? So how do we give you advanced feature engineering with advanced data transformations coupled with interpretability, documentation, and giving you and automatically generating the final pipeline, which is a production-ready model that can be easily deployed into your production environment, yet giving you control to fine-tune things. So by no means we want Driverless AI is a black box. We'll talk more about how recipes can actually be used to give you full control over what goes as part of each step of the experiment. But at the end of the day, the second generation we think of Driverless AI as the second generation because it encapsulates advanced feature engineering and because the final model pipeline allows you to actually deploy a model that not only does the scoring, but also does the feature engineering. So it's a full encapsulation end-to-end, and it's extremely robust, extremely simple to deploy, where you don't actually have to do any additional tasks by hand. And then finally, the third generation, which is a combination of Driverless AI and H2OQ, it's all about democratizing AI. So it's really taking the concept of models and rather than delivering models, it's delivering AI applications. So things such as automated data augmentation. We talked about your data being that lever, or your data, using data as your leverage. Now, how can you really apply AI where it can provide additional insights about your business? It can look at your data, it can identify gaps in your data, and it can even go out there and make suggestions. How do I enrich and how do I augment my internal data sources such that I can have a more robust and a more more holistic, more insightful view of my business? So rather than you having to ask questions, it's the ability for H2OQ to push answers for questions that you may not even thought of asking because you didn't have the data in the first place. And now that we understand the landscape of automated machine learning from first generation all the way to third generation, now if I come back to this picture that we just explored in a few slides ago, and now let's look at distributed machine learning with H2O AutoML. So the same principles apply here, but rather than doing everything by hand the way we walked through this, now you're actually able to go through a few simple steps of loading the data. So you have a training data and you have a test data set, specifying the response and the predictor variables, and then letting AutoML run. You can specify the stopping criteria. So in some cases, you want to specify the amount of time that you want AutoML to run. So it could be an hour, could be a couple hours, or maybe the criteria is when your performance metric converges. So for instance, if I'm looking at AUC score and the moment that my AUC stops increasing and becomes more of a flat horizontal line, at that point my AutoML has probably converged. It found the best model. It can no longer tune the model beyond that, and that's a good place for you to stop. And then everything else that follows that process is exactly the same, where you have the leaderboard and you can now start looking at the individual models or even ensembles of different models that H2O AutoML has produced for you. But the net result here is the same H2O model or the modular object as we've seen before. The only difference is that in the first case, you coded everything by hand, leveraging the distributed data and distributed computing power, whereas here, H2O AutoML took over and it checked for all these different scenarios for you. But the net effect is exactly the same, where you end up with an H2O model object. Now, what's missing in this picture here is that anything to do with feature engineering is still a very manual process. And that's where H2O Driverless AI really comes in. And Driverless AI, if I was to really net out the innovation within Driverless AI, is the genetic algorithm. So it's the idea for you that we allow you to, in a single run or a single experiment, you bring the data into Driverless AI, and then you can let it run on its own with some parameters that you would specify, or you can actually take full control, and we'll talk about that in just a second. But in its simplest form, when you bring the data into Driverless AI, you then start the experiment. And what happens under the covers is that it runs through a genetic algorithm that looks at your data. It understands the original features in your data, and it starts the genetic algorithm that goes through feature evolution at every iteration, every step of the way. It creates models, and it fits those models on your data to see if the intermediate result. And that process repeats many, many times. So it's an evolutionary algorithm, because at every step of the way, whatever features, whatever newly generated features have contributed to a lift as you move from one iteration to the next, those features may actually be kept, and those features would live on. Other features that have not contributed to a lift would eventually die off, and we would just discard those features. So at the end of the experiment run, through all the advanced work that happens under the covers, what you end up with is you actually get an extremely robust and extremely performant model, which could either be a single model type, which can either be a single model type, such as maybe it's an XGBoost model or a live GBM model, or it can actually be an ensemble. So in some cases, depending on the settings and the parameters that you choose, you can actually have an ensemble that incorporates an XGBoost and a live GBM and a GLM and other model types in order for you to get the most performance, the most accuracy based on the metric that you've selected. In addition to that, you also have all of the artifacts that come together with the scoring pipeline, which is the automated model decommunication, as well as all of the explainability and interpretability of that model. Now, just a little bit on the extensibility of Driverless AI. This is where we really want our customers, and we really want the data scientists to feel that they have full control over the process. And this is where we think of Driverless AI as basically this engine, the framework that allows you to bring your own code and your own recipes. And under the covers of Driverless AI, we have, on the left-hand side, we employ the latest innovations from the open source community when it comes to the actual machine learning models and machine learning techniques. So things like, obviously, the H2O core, so everything that we just talked about is part of what Driverless AI uses under the covers, but so does LightGBM and XGBoost and Keras and TensorFlow and all these other libraries that we use, in tandem or in combination in order to produce, the most robust and the most accurate modeling results possible. But not only that, we also open up the platform to custom recipes where if you're an advanced data scientist and you have Python skills, you can now create your own transformers, algorithms, and scores to enhance the capabilities of the platform. And the idea there is that you may be looking at, maybe there are some domain-specific data transformations, or maybe there are some specific data, domain-specific data prep techniques that you want to apply. Maybe there are additional models, or maybe there are some scores that will really designed to optimize your business metrics. You can actually now incorporate all of that into this end-to-end run and the end-to-end machine learning pipeline that Driverless AI employs. In a simple example, we actually have a customer that is working on an AML project, anti-money laundering, and what they've discovered is that the time between an account getting opened and a transaction that lands in that account could actually be a signal towards a money laundering behavior. So that is something that is very domain specific, and this is, this could be applicable in their, or this may only be applicable in their case, but not so much applicable for other types of use cases. So now they can actually take this, what seems like a fairly, logical thing to do and a fairly simple way to represent, your data transformation. They can actually now take that, and with very simple piece of Python code, they can actually now pre-process the data on the way in to look for the dates and to look for the time difference between account being open and a suspicious transaction landing in that account. They can employ different transformations. They can bring models and scores that are really optimized for that specific use case. And that is, any of those recipes are obviously proprietary, and those are IP of the customers that use them. But in addition to that, the H2O catalog, we have by now there's probably more than 120 or 130 different recipes, which is this is an open source catalog that every customer can go in, or anybody can go in, and you can really start playing around with all these different models, scores, transformers, and data recipes. You can bring them into Driverless AI, and you can leverage them as part of your end-to-end machine learning cycle with Driverless AI. And if I now put all of this together, so the real value here is that Driverless AI allows you to condense the amount of time that it takes for you to go from a business problem to a fully ready production model. And if I go through this process, on the left-hand side, you start with a data set that could be sitting on HDFS, maybe or maybe any other data source. You then go through the data prep process. You look at the data through automatic visualization, which is one of the core features of Driverless AI, and it's really designed there. So it's not a BI way to visualize your data, but it's really from a data science point of view, helps you to understand your data shape, the outliers, any missing values in your data. You can then apply your data recipes to pre-process this data. If maybe there's some outliers that you want to discard, and maybe there's missing values that you want to replace, you can bring in the additional scores, algorithms, and transformations, which are domain specific, and then you employ the entire the evolutionary algorithm that now takes all of the best of breed capabilities of Driverless AI. It incorporates your recipes, and it now produces this final final scoring pipeline that includes the model, has the actual compiled code that allows you to deploy that scoring pipeline, but also provides you with full model documentation as well as the interpretability such that your model risk and model governance team, model validation team can be comfortable with the fact how that model is going to perform if you will actually start making business decisions based on that, based on this new model. And that's where trust in AI becomes extremely important. So again, H2O has been pushing the boundaries of what's possible with MLI or machine learning interpretability by giving you both global explanations, local explanations, disparate impact analysis, and using all the latest techniques such as line, K-line, Shapley values, PDP, and many other techniques when it comes to model explainability, to give you the confidence that the result that the model is producing, for instance, it's not discriminating against any of the protected classes, and so on and so forth. And we actually have some really interesting case studies where customers, beyond using Driverless AI as a model building tool to accelerate the model building pipeline, some of the key time savings that they're finding is exactly with machine learning interpretability, because the ability for them to really understand the fine details, how this model was built, what features were generated, what is the variable importance, and having full model documentation available to their model risk and model validation team just allows them to shave months of time that otherwise would have to be a very manual process before that model could ever be put into production, given the sensitive nature and the regulatory environment in those financial institutions. So speaking of model deployment now that we understand how the models are actually being built and how you go about interpreting those models, now let's take a quick look and actually and look at another example of putting those machine learning models into production. So starting on the left-hand side with model training, you've got the various data science environments at the top, which could be R or Python, and then you can have Jupyter, RStudio, and other environments there. You then go through the model building phase, which can either be used or which can either leverage H2O core using the cluster, the distributed cluster, such as Hadoop, Spark, or Kubernetes, or you can leverage H2O Driverless AI if you're looking for more of an automated platform where the platform allows you to automate a lot of the pieces of the machine learning lifecycle. In both cases, what you end up with is you have the H2O model or the module file, which basically gives you the full representation of the model and the only dependency is the runtime itself. So now, as you look on the right-hand side, what you have is you have the Java module library or the C++ module library, and these are two different runtimes that you would leverage depending on your deployment environment. And now, given the Java and the C++ runtime capabilities, you can obviously deploy this into any Java-based environment. You can call that model through REST API, or you can use language bindings on top of the C++ runtime with R, Python, .NET, and many other environments many other languages that provide language bindings on top of C++. And now you actually have your model, which can be deployed into, could be specific decisioning systems, decision support systems at the bank. We have customers that are doing very simple things where they actually have a model scored from an Excel spreadsheet. What I would say is a very, maybe very basic or very primitive way to use the model. But if this is what you use for your, for your decision making, then the robustness and the lightweight of the H2O model can really be invoked from Excel or from any other data decisioning system. So, for instance, Hive, Kafka, Spark, they can all easily tap into the Java way or the REST API way of invoking the model. And that's a very simple, very straightforward way for you to go from model training on the left-hand side to storing those models into a model repository where every Mojo file is completely independent and has no dependency on the training environment. So once the model is trained, you can literally take that model and you can now version that model independently from the environment where the model was trained. And then once that model gets approved by your model risk management and model validation teams, you now can actually push that model into your production environment based on Java or C++ library runtimes. So with that, we're coming up to the end of our technical discussion here. I'd like to spend a few minutes talking about some of the success stories in financial services. So we have many different customers across the banking industry, and some of the prevailing use cases, some of the most interesting use cases really have to do with, for instance, credit risk scoring as part of the payment technology, or loan credit risk, as well as mortgage default as part of retail banking. And we have many customers ranging from Wells Fargo, Capital One, Franklin Templeton. Actually, we'll talk about some of these use cases in a second here, that leverage H2O technology as part of their enterprise-wide AI initiative. So in the case of Wells Fargo, for example, they have a variety of use cases ranging from anti-money laundering, predictive banking, customer 360, transactional fraud, and they use H2O, both H2O Core on the open source side as well as Driverless AI. And the biggest value that they see beyond the ease of use and beyond training extremely robust and extremely accurate models, but it's that explainability. So big factor for Wells Fargo was the challenge that going through model risk validation and model risk and model validation teams to get new models approved to deploy into production was extremely tedious and consumed weeks, if not months of time. And now by being able to leverage MLI and being able to leverage automated documentation that you get from Driverless AI, they're now able to shave this time by a factor. So as a result, they get more models into production faster, which influences and is able to actually impact the business at a much greater speed than before. Another customer, Franklin Templeton, is actually, again, they have a variety of use cases, customer segmentation, next best offer, loan default prediction, and many other ones. And what they found really exciting about H2O technology is the whole concept of custom recipes with Driverless AI. They have a very interesting use case where they're trying to estimate the prepayment and default risk of underlying loans in their mortgage-backed security portfolio. And for that, they really needed to be able to take advantage of the automated machine learning that Driverless AI delivers. But they had to get under the covers, and they had to write their own custom recipes in Python that allow them to optimize the metrics and leverage the algorithms that gave them the advantage in terms of estimating that prepayment and default risk for their loans portfolio. Very interesting use case, and after doing evaluation of several different technologies, they really came away, what I'd say, wowed with the ease of use and the speed, the time to value that Driverless AI enabled them to do, yet giving them the full flexibility and the ability to really own the data science experience by creating their own recipes and making sure that they're in full control of what happens under the covers. So hopefully these two examples are interesting and relevant. Just as we're coming up to the end here of our webinar, 2 words about H2O.ai as a company. So we're a global company. We have about 220 AI experts around the world, and we're extremely passionate about our customers. So just these 2 examples obviously speak to the work that we've been doing in the space, but many other customers ranging from Goldman Sachs, Genentech, Kaiser, Roche, Wells Fargo, and so on and so forth, spanning many different industries. Financial services is definitely one of the key industries where there's a lot of opportunity for AI to be incorporated and there's a huge uptake. But beyond financial services, we're also extremely active with insurance, with healthcare, retail, telecom, manufacturing, and so on and so forth. And at the core of our team, we've got an extremely, incredibly talented team of Kaggle grandmasters. So, that's one of the things that H2O is really known for, is about hiring the best and the brightest talent out there. Kaggle is a wonderful competition platform where people can really build their skill sets. They can compete as novices in the data science arena, and over time they can grow through the ranks. And the Kaggle grandmasters are about the top 150 individuals globally out of about 100 or maybe 200,000 people that enroll in Kaggle. And we, today we employ over 10% of those Kaggle grandmasters, including folks in the top 5 and the top 10. And these are the people that are very, very vocal and very much front and center, both helping with H2O products as well as engaging with customers in order to help solve their challenges. So hopefully this was a worthwhile use of your time. We got about 14 minutes here left for questions. Again, just a recap of some of the key takeaways from today's session. Hopefully you've been able to go through some simple examples how you can train machine learning models at scale on top of big data platforms, how to apply AutoML or automated machine learning to accelerate your model development, and then look at a few examples of actually taking those machine learning models and deploying them into your production environment. So with that, I'd like to thank you. And Shabar, if there are any questions on the line, more than happy to take them now.
Thank you, Dimitri. We do have some great questions coming in the chat window. We'll try to get through all of them with time permitting. I'll go through the questions. How does driverless AI perform against a manually generated model? Do you have any benchmarks?
Yes, so I think this is obviously a very loaded question because, and the answer, it depends. We do have benchmarks, but benchmarks, I don't think that benchmarks are a very accurate way of assessing performance because there are just so many things that can be tweaked in the machine learning pipeline. So A, we talked about the feature engineering process. B, we talked about feature selection, model tuning. And what I would say is that Driverless AI actually allows you to fine tune every single step of the way. And if you want to add some additional capabilities beyond what's available out of the box, that's when the custom recipes come in, and you can actually pull in the model that you would like to write by hand into the genetic and the evolutionary algorithm that Driverless AI employs. So now you can almost think of this as you can offload the feature engineering part and the feature selection part to Driverless AI to do the best it can to identify that signal and separate from the noise. And then if you already have a machine learning model which you truly believe is the best way, and is already tuned to perfection, you can actually have that plugged into your pipeline, and you can either let it compete against other models that Driverless AI would employ as it goes through the experiment, or you can actually disable every other model and only use the model that you've built, that you've delivered through the recipe, with all the fine tuning that you've performed. So I would say we do have benchmarks, but those benchmarks are highly dependent on the environment, on the model type, on the data set. So it's not, I wouldn't trust a benchmark in isolation. I would always go and try to understand how can I leverage Driverless AI and let it do what it does best, yet have full control over the model types and the tuning and the selection and so on and so forth.
Great. Can H2O be applied in Google Cloud Platform?
Yes, absolutely. And again, this is a little bit of a loaded question because there are many things within GCP, but the short answer is yes. Both H2O open source as well as Driverless AI can be deployed, just running on their VMs. So if you can provision a VM, in GCP, you can run it that way. Both platforms can run on Kubernetes. So if you have access to Google Kubernetes service, you can have H2O clusters run on top of Kubernetes. You can also have Driverless AI run on top of Kubernetes. So absolutely yes. There are different configurations that we're happy to explore, depending on the scenario.
Great. How are you running prediction from an H2O model in a serverless mode such as Lambda or Cloud Run?
Yeah, that's an excellent question. So specifically with Lambda as an example, you can actually, with Driverless AI, and you can do this with the module by default, but you can, even with Driverless AI, we actually have a single-click deployment into AWS Lambda. So if you have your AWS credentials, you can specify them as part of a model deployment step within Driverless AI, and then with a single push of a button, once your experiment completes and you have that final model or the module generated, right, with all the feature engineering and the model ensemble and everything is tuned, and basically it's a self-contained model, that model can now be deployed with a single click of a button into AWS Lambda, such that if you have other other systems or other services hooked up to invoke the Lambda through an API call, the module will get invoked as part of that API call. So it's extremely flexible, either single click deploy, or you can do that manually by taking the module out of Driverless AI or the module out of the H2O open source and doing a manual deployment. We have all of those steps documented in our documentation.
Great. Does H2O use Python, PySpark libraries, or customized H2O packages?
Do we use Python, PySpark, or customized H2O packages? We use, so the models, the H2O core, and I'm assuming that's a question about H2O core. If not, please provide some additional context there. So the models themselves are written in high-performance Java code. That being said, you then have API call, which is pure Python API call, or our API call, that allows you to invoke those from your Python front end, from your Python programming environment. So the execution happens in high-performance Java. The library itself is available through a Python package that can get linked and imported into your Python environment.
Great. Can I have online models that continuously retrain once in production?
Yes, that's something that, so you can do this, and not something that you would enable with a single click of a button. Let me just say it this way. But for instance, with Driverless AI, you have the module that has been that has gone through the first iteration. You've trained the model. You have the module. You can deploy that module, and now the new data that comes in while you're running this model live would then have to get collected, and you can invoke a rerun of that model to retrain that model. Now, one thing that I should add here is that in the case of Driverless AI, the tool has a GUI, and it's a front-end point-and-click tool, but everything that is exposed through the GUI is actually orchestrated at the REST API level, and we provide full Python and our client such that you can actually use the tool programmatically. So in case where you would want to have a model that runs in production and gets automatically retrained, you can absolutely orchestrate that through the use of the Python client, and the Python client would essentially then invoke Driverless, collect the new data that is coming in online, and invoke a retraining of the model on the back end. Once the new model is retrained, you can redeploy that model. So it does require a little bit of coding, but the ability for you to do that is there, absolutely.
Great. Looks like we have time for one last question. Does a data scientist still need to manually create model features when using H2O driverless AI?
Great question. And I would say as a data scientist, the answer is probably no. But as a domain scientist or as a business stakeholder, the answer is probably yes. So keep in mind that feature engineering that driverless AI delivers, it's more of a statistical feature engineering rather than domain-specific feature engineering. Now, that space is getting a little bit, there's a little bit of an overlap, especially with the custom recipes, where through a custom recipe, you can actually inject some of your domain knowledge into a recipe and then use the recipe to do your data prep and to do the data transformations as part of feature engineering. But in a broader sense of things, what I would still suggest is that your domain scientists or the business analysts who really understand the domain, the business problem that you're trying to solve, would work with maybe data engineers to help prep a modeling data set that has some basic, baseline features, and then that data set is then passed off to the data scientist who's working with Driverless AI, and from there, the data scientist can leverage Driverless AI to do feature engineering or can inject additional domain expertise through custom recipes. So I don't see Driverless AI completely figuring out your business problem. I think we're still a little bit of ways, have some way to get there. But once the domain scientist has defined the data set and has identified the core features that are needed, from that point on, the data scientists can fully leverage Driverless AI with recipes to perform the work rather than having to do any manual feature engineering.
Great. I think that's all the time we have for questions. Thank you, Dimitri, for taking the time today and doing a great presentation. I'd like to say thank you to everyone who joined us today. The presentation slides and the recording will be made available on our Bright Talk channel. Have a great rest of your day, everyone. Thank you.
Thank you, everyone. Take care now.